There are brilliant people working with students, brilliant students, on research projects, some of which are very successful and they discover some new information. How does that new information become known to the rest of the world? The normal procedure is they write a scholarly paper about what they did. The scholarly paper is usually about 20 pages, and it looks like part of a magazine, but it comes out in these things called journals. Okay? And the journals are published based on something called peer review. Who knows what peer review is? What is a peer? An equal, okay? It's an equal. So for instance, my specialization has to do with satellite control systems. Alright? I'm a peer for satellite control system people. Satellite control systems experts. So when I discover something new about how to do satellite control systems, I write a paper about it. I describe what I did. Then I send it to the journal. The journal takes the paper. They don't decide whether it's good or bad. They don't know. They send it out to other experts that are in the same field. And they ask them to read it, usually 3, sometimes 5, sometimes 2, but usually some number like that. And they say, please read this paper and tell us your opinion. Is this good? Is this important? Is it something new? Is it something old? Is it not so good? It's not so important. If the peers say this is good and this is new and this is important, then the paper ends up getting published in the journal. Now, at that point, it becomes public information. When it's in the journal, the other experts in the field all around the world read the journal. And they say, oh, that guy Monk, he discovered this thing. This is interesting. Then maybe it changes the way they do their research a little bit. Now that I know this, I can do this next thing. So all of the leading researchers all around the world are talking to each other all the time. Every time somebody learns something new, discovers something new in their research, they send it for peer review. A few people know about it, but not many, because sometimes there's a lot at stake in being the first one to discover something. It's very important to be first. So only a few people see it at first, and they make an opinion. And if it's good, then it gets published in the journal, and then everybody sees it. Okay, now, after it's out in the journal for a while, pretty soon a lot of people know about it, and eventually some professor somewhere, like me, or one of your professors here or something, decides, I'm going to write a new book for students, and I think I'll put this information in the book. So when it comes into the book that you have in your class, like EAS 208, the book for that class, the information in there is already at least many years old. Now some things, if it's real basic physics, it might be centuries old. Maybe humans knew about this a long, long time ago. Some things are newer. Maybe we only knew about it 10 years ago, but it's still old. So if you really want to know what the state of the art is, what is the best thing going on right now, the latest information in your field, what you have to be able to do is read these journals. These journals are very specialized. They're for the experts in the field. Okay? Only later, after it's in the journal, does it become more common knowledge for everybody in the book. Any question about that? So these journals are very, very, very important to the highest level research, the newest research. This is where it appears. If you want to be an expert, if you want to be a scholar, if you want to be a professor or leading researcher, somebody like that, you have to read journals, and sometimes you have to be able to publish your own articles in the journal. It's a matter of prestige for people in the field to publish an article in a journal, because it means you did something important, you did something new. And the peers, when they reviewed it, they said, yeah, this is good, this is new, this is important. So they agreed. So if you have an article that appears in a journal, this is very special. Okay, so ASME has 27 journals for different specialties. The first one is the most general one, this Applied Mechanics Review. So I started this description of peer review to come back to this word review. In this title, what the word review means is, this is sometimes what's called a review article. So this is an intermediate step between the journal and the books. So let's say somebody just invented, I don't know, nanotechnology. So he publishes the very first article on nanotechnology. And now it appears in a journal. And other researchers all around the world, they get the idea, oh, this nanotechnology, this is really interesting. Now they all start doing research. And one after another, he publishes an article, he publishes an article, she publishes an article, he publishes an article, she publishes an article. All of a sudden, there's 100 articles about nanotechnology. The total amount of information starts to get big, it starts to get difficult to keep up. So every once in a while, somebody somewhere says, okay, wait a minute, I have to make some sense out of all this. And they take maybe 200 articles, 500 articles that appeared in journals, and they condense it all into one big article to explain how it all relates together. Here's the history, and here's how it all fits together. That's called a review. The review. So one of the journals that ASME publishes is about applied mechanics, like 207, 208, those kinds of courses. New discoveries, new research, but they're review articles. Take one field where there's a lot of new papers, combine all that information and write a review so that everybody can understand how it all fits together. Okay? Who thinks they want to go to graduate school? Only one? Only one guy wants to go to graduate school? No? It's too simple. You're not thinking about it. Who wants to go to graduate school? Nobody wants to go to graduate school. Who wants a master's degree? PhD. Okay, master's degree, PhD, you have to go to graduate school, which is good. Now, when you go to graduate school, you have to write something called a thesis. A thesis. That's part of the degree requirement. A thesis is something like a journal article. Right? That's when you do some research, some original research of your own. And maybe you make a little discovery that pushes the knowledge that humans have out a little bit farther. It's really exciting. Right? Journals are really exciting. Here's the limit of what humans have figured out. In the last 1 million years, we figured out a lot of stuff, but not everything. So here's the boundary. And how does that boundary move out? It moves out by little research projects scattered in labs all around the world. And every time one of those research projects moves that boundary out a little bit, they write about it in a journal. That's where you learn about it. You want to know where the limit of human knowledge is? Read journals. And when you want to see that limit move a little bit, which is terribly exciting, it's terribly exciting to see that boundary of human knowledge move. Is there anything cooler that you could possibly do in your life than watch the boundary of human knowledge move? Yes, there is. You can help it move. That's even cooler. But watching it move is pretty cool. Journals is where all that information gets transferred. It's great. Okay, so applied mechanics reviews. This isn't new research. Reviews are when you collect things that have occurred in journals and you report on them. You make sense out of a bunch of them. Now let's move on to another.
I have a question.
Yes.
What is that? The price of it? The price of
Yeah, that's a subscription price. So you don't get these journals automatically just because you're a member. You get the general magazine automatically if you're a member. Then, if you're a member, I think you can select one division. We'll talk about divisions in a minute. And if that division publishes a journal, then you get that journal as part of your membership. Okay. Okay, so that was applied mechanics reviews. This is applied mechanics. So this is where, when some individual person makes a new discovery in applied mechanics, they would publish their new discovery in applied mechanics. Applied mechanics reviews is when somebody acting sort of like an editor collects a whole bunch of new discoveries within one narrow field and writes a summary. That's a review. But this is each individual new discovery, okay? Maybe tonight you go home, you start cooking dinner, something very unusual happens in your kitchen. I don't know what. But the heat comes into your pan. It does something that you've never seen before, some new physics. You write a new paper about it. It's mechanics, right? It has to do with heat transfer. Send it to Journal of Applied Mechanics. And they publish it and your name gets famous. right? Science literature, math literature, it's full of the names of people, isn't it? You haven't gotten too far yet into your degree, but already you know a lot of people. You know the name Newton, I think. You know the name Einstein. Right? You're going to learn more and more names. People get famous because they discover something that no one else had discovered before them. Okay? Here's your chance. The Selene coefficient. The Caspar theory. Okay. Journal of Biomechanical Engineering. So, throughout all of engineering, I think, in every engineering field, there's some applications that have to do with human medicine, because that's an enormous business. We talked about automobiles before. Medicine is another one. Everybody, sooner or later, gets sick. And when you're sick, you want medicine. Right? So there's a huge business. Everybody wants to improve human medicine. It's good. It's a good thing. So the Journal of Biomechanical Engineering. Something I didn't point out on the first two, but let me back up and I'll just point it out. I talked about peer review, right? Let's look at who's the editors. The editor of this journal, Journal of Applied Mechanics, is this guy, Robert McMeeking. It's a guy, it's a professor, just like me. He comes from the University of California in Santa Barbara. Okay, so he's the editor. So if you have an idea you want to publish in this journal, you send it to him. Then he secretly sends it to peers for the peer review. Right, 3 or 4 people that he selects that he knows are experts in the field. They tell him their opinion secretly. That happens in secret so that you don't know who they are. That way you can't influence them. Excuse me, that took my throat. Yeah, I think I agree with Caspar. I think if you want to talk, we had this discussion last time. If you want to talk, go outside and talk. It's okay with me. But if you're going to stay in the room, please be quiet. Okay? Do we understand?
Yes.
Yes? On the end of the row there. Hey, please go outside now. You're not listening to me anyway, so please go outside. You know I'm talking to you. Go outside. I think you're very rude to your classmates. They're trying to listen to me and they can't hear me because you're making too much noise. You can come back at 3 o'clock. Okay. I hope I don't have to do that again. I really don't enjoy that. But it's unfair to those of you that are trying to listen. If you don't want to listen, I don't care. But leave the room if you're not going to listen. Alright, so this guy who's the editor, he's just a professor. This is the whole idea of the peer review. Who decides what's important in the next piece of science? It's not the government, it's not the big business. It's the experts in that field. Those are the peers. All the people that work in applied mechanics write a paper to this guy, and he shares them with each other. And if the peers say it's good, it gets published. Okay? Who decides in biomechanical engineering? Another professor. This one happens to be at the University of Pittsburgh. Just another university. Underneath these editors, there's usually maybe 8 or 10 what are called associate editors. And usually when the papers come in, they divide them even more specialized. Right? Biomechanical engineering sounds very specialized to most of us. But if you work in the field of biomechanical engineering, then there's even more specialization. Maybe your specialization is legs. And another guy's specialization is blood flow. And another guy's specialization is the elbow, or the wrist, or who knows what. Dialysis machine, very mechanical machine, very specialized in the pump. We have red blood cells in our blood. If you break those cells, it's very bad, but you have to pump the blood. So how can you pump the blood without breaking those cells? It has to be very delicate. It's tricky. It's hard to do. It took humans 1 million years to figure out how to do it. Right? But all those different specializations are under biomechanical engineering. So this guy has associate editors, and they're just professors and other experts scattered around different hospitals. right? And the idea is each group has its own peers, its own experts, and they're the people that have the best idea of what's the next important science. They decide what will get published in the journal. If you join the society, you can become one of these. Here's the next one. Computational and nonlinear dynamics. Computational and nonlinear dynamics. What do we mean by computational dynamics? Who's taking 208 right now? Not everybody wants to admit it, I know, but okay. So in 208, you're learning some dynamics. The dynamics you're learning, everything that you need to calculate, there's an exact equation for you to calculate in that class. But those problems are simplified from a lot of real-world problems. A lot of real-world problems are more complicated. You can't make an exact calculation. Right? For instance, what if I ask you, what's the answer to this? Okay. What if I ask you again, what's the answer to this? How do you know that? Because you remember it, right? You memorize it. Okay, so let's make it a little bit more interesting. So you don't know this, right? I don't think. Anybody had this one memorized? Okay, good. If somebody had this memorized, I'd be nervous about you. Okay, so there's no reason to memorize it, right? Why not? Because you can calculate it. And how do you calculate it? You punch a button on your calculator, right? But if you didn't have your calculator, how do you calculate the cosine? And you measure, and then take the division, right? So that's not perfect, because your measurements are never going to be perfect. It's not perfect, but it's a perfect idea. It's just that you can't do it perfectly, because you can never have a perfect measurement. But yeah, it could be perfect. What's the series approximation for this? Who knows? Well, first you have to convert this to radians. So this would equal to 1. I'll start you with minus, right? Alpha squared over 2 factorial plus alpha to the 4th over 4 factorial minus. That's the answer. Nobody's going to go out to infinity though. So out here after about 4 or 5 of these, okay, close enough. Stop. That's the difference between dynamics and computational dynamics. Computational means it's not exact. It's something you're going to calculate. Now this isn't such a great example because actually this series is easy enough to calculate that you can go a long way and have a very precise answer. Even though it's not exact, it's still very close. But a lot of dynamics problems you can't get very close, right? So let me give you another example. What's the basic equation of dynamics? F equals ma, okay? And what does this stand for? Force. Okay, so last night I flew home from Kuala Lumpur. I flew back to Hanoi. I'm on an airplane. Oh, what a perfect airplane. Good drawing. Okay. There's the airplane I was on. That's not actually a photograph. I know it looks like a photograph, but it's just a drawing, believe it or not. So here's the airplane. So what are the forces? I know that airplane satisfies this equation. And I know that somebody figured it out well enough for the airplane to take off 1,000 miles away, fly 5 miles over the ground at 1,000 kilometers an hour, and it actually got to the right place. Right? And I'm standing here. I'm here to talk about it. I'm not lying in a hole in the ground. So, somebody figured it out. But what are the forces?
Gravity.
There's gravity. Okay, let's talk about that one. How much gravity was acting on the plane? Right? The force of gravity would be mg. What's m of the plane? You don't know. Nobody, right? Have some idea. But there's a lot of suitcases. There's a lot of people on board. Some kind of fat. Some kind of skinny. Some are little, some are big. Some of them had a big lunch before they got on. Some of them didn't. They were probably sick. They were nervous, so they didn't eat anything.
So we can estimate.
Right? Some people had some hand luggage. They brought home a durian. Pineapple. Yeah. What did that airplane know? Who knows? Who knows? Nobody knows exactly, right? Okay, so how do I calculate this? That's the easiest force of all, is gravity. That's the easiest one. We've known about that one for 400 years. But we can't even say exactly what the gravity force was on that airplane. We don't even know. What other forces are there? There's air resistance going this way, right? A force of air resistance. There's the gravity force pulling down. What other forces? There needs to be something going up, right? So there's lift. What else? There's a propulsion, right? You need a propulsion. Now once the plane is flying along at a nice altitude, we like it to just cruise along at a steady speed, right? So what should happen in this equation? Yeah, this part should go to 0. Not in the beginning and not at the end. But in the middle, you want to just cruise along and hopefully there's no acceleration. So there needs to be, all of the forces that go that way have to be offset by something going that way, so it adds up to 0. All the ones going this way by something going that way to add up to 0. There's also forces this way that need to add up to 0. Right? So the airplane has a lot of so-called control surfaces at the backs of the wings. There's little cutouts. You can move them up and down. It creates different forces on different sides. There's one in the back of the tail. Does the same thing. There's another one back here. Does the same thing. Those are called control surfaces. And they all have to get balanced out to make this equal to 0. Okay? So how can we calculate what those are? Actually, we can't. Yeah, we can't calculate them. So we have, on the airplane, there's a lot of little sensors that measure what's happening all the time, and they make adjustments in real time. If they sense that the plane is sinking a little bit, they make an adjustment that increases L. If it's slowing down a little bit, make an adjustment that increases the in-drawn engine. The thrust of the engine, right? Increase the thrust. Whatever it takes. But it's all calculated. It's all calculated over and over again. It's not predicted. We don't really know. It weighs a different amount. Yesterday was hot. There's more moisture in the air. In the wintertime it's cold. The air has less density. More density, less density. Sometimes there's water in the air. Sometimes not water. Sometimes there's wind. Sometimes there's a big storm. Right? Sometimes the sun is shining. Sometimes the sun isn't shining. It all makes a difference. Okay, so that's the idea, is that for a lot of real dynamics, the theoretical prediction is useful, but it's not precise. Not because the equation isn't perfect. The equation is perfect. The problem is, we can't substitute perfect numbers into the equation. We know the gravity force is mg, but we don't know what n is. So that's the idea, is we have to calculate it. It's going to be an approximation. So I'm mentioning a lot of this, those of you that are going to take the higher level language class. That's why that higher level language class is part of the curriculum. Because in fact, most problems can't be solved theoretically very well. They can only be calculated. So we have to know how to calculate. So here's a whole journal based on computational dynamics. Also, nonlinear dynamics. What's nonlinear? What does it mean to say nonlinear? What's the opposite of nonlinear? Linear. Okay, and what does it mean to be linear? So you have a variable x and some function of x. What does it, if the function is a linear function of x, what will this plot look like? It looks like a line, a straight line, right? It doesn't have to go through zero. Maybe it's like this, or maybe it's even like this. But it looks like a straight line. And what's the really critically important implication of having that straight line?
For each value of x, we get only one value of f.
Yeah, it's single value. That's very important, right? So for each value of x, there's only one value of f. That's very important. There's another thing that's really important about predictability.
The slope.
The slope, right? So for every time I change x by a certain amount, no matter what the starting point is for x, the function changes by a predictable amount. Right? Let's go back to our airplane for a minute. Think about how important that is. So let's say I detect that the airplane starts to sink a little bit. It's going down. I want to increase the lift to make it come back up. The lift is proportional somehow to how fast it's going. The faster it goes, the more air blows over the wing, the more lift there is. But is that a linear proportionality? Actually, it's not even close. Right? For one thing, the amount of lift depends on the density of the air. And the air is much denser at sea level than it is at high altitude. At high altitude, if I go high enough, there is no air. There's no lift. The spaceship doesn't stay in the air because it has lift. It doesn't have any lift. It stays in the air because it's going so fast that actually it's falling the whole time. It's trying to hit the earth, but it's going so fast sideways it keeps missing. And it just goes in a circle all the way around the earth. But it has no lift. It's falling towards the earth. If you could calculate the velocity vector of the spacecraft, you would find that it's falling to the earth at g. It's falling to the earth at g all the time. But it goes so fast sideways that instead of hitting the earth, it swings out here, and when it falls, then it moves down a little bit, and now it wants to fall this way, so it moves down a little bit. And if you get it just right, you get the combination just right, the spacecraft actually just goes in a circle. But there's no lift. But on the airplane, there's definitely lift. That's the only thing holding the airplane up, is the lift. But the lift is much lower at the high altitude because there's not as much air. So the change in velocity you need to increase the lift a certain amount is much different at a high altitude than at a low altitude. That's nonlinear. In order for me to calculate how much change of velocity I need, I also have to know what the altitude is. But here, if I had a linear function, if I know that I need to have, say, 10 more units of lift, I can get 10 for the same change in x. Will give me 10 no matter where I start. It's always the same change in x that gives me a change of 10 in the function. But for lift, it's not true. To get a change of 10 lift, it's much different at sea level than it is high altitude. It also depends on how fast I'm already going. At slow speed, the lift doesn't change as quickly as it does at higher speed. Because part of lift is proportional to velocity, but it's also proportional to the square of velocity. So at higher speed, I get a bigger change in lift by a change in velocity, the same change in velocity. It's the same thing with drag. Did anybody watch any of the Tour de France? Like bicycle racing? Yeah, I like watching it. I think it's kind of fun. So it just ended on Sunday, right? An Australian won. First time ever. It's kind of interesting. But when you watch them ride, almost all the riders stay in the back, right? There's one guy out front, and he's huffing and puffing, and he's got all the wind blowing on him. And the drag, this resistance force, same thing. It's proportional to velocity and also to velocity squared. So when they go faster and faster, the difference in the amount of work the guy in front does compared with the people behind him gets bigger and bigger. It's not linear. The advantage of being in the back is much bigger when you go fast than it is when you go small. That's non-linear. Almost all dynamics, almost all important dynamics is non-linear. Okay. I got a little long-winded there. That was a nonlinear discussion. And who edits that journal? A guy from the University of Illinois at Chicago, another university. Those guys are volunteers and they change. Each guy does it for about maybe 3 years, 5 years, and then somebody else takes over. Okay, Journal of Computing and Information Science and Engineering. Right? Edited by another guy from University of California at Davis, another university. Journal of Electronic Packaging. Right? There's a fancy one. This is also a huge business. Again, most people probably don't even think about it. When you think about electronics, you think about the electrical side. But that generates a lot of heat. And also, we want to make things smaller and smaller. And how does your cell phone end up looking like it is and it doesn't catch on fire? There's a lot of big problems with electronic packaging. It's a big industry. Journal of Energy Resources Technology. Okay, I think that's another one we didn't discuss. But different kinds of energy: wind, solar, coal, nuclear, oil, natural gas. What's the primary source of electricity in Vietnam? What is the primary source of electricity in Vietnam? What is the energy that's used to create electricity? Who thinks it's hydroelectric? Okay, who thinks it's nuclear? Who thinks it's coal? Yeah? Who thinks it's petroleum? Natural gas? Solar? Wind? Does Vietnam have nuclear power plants? Who thinks you have a nuclear power plant? I visited. I know you have one. I've been inside of it. Okay. I don't know what the top source is. Maybe that's another nice little homework assignment. Go figure out the percentage of the source of electricity for the country. Right? Because this is a big problem for every country. Did everybody hear what Germany recently declared? Germany just did an amazing thing. Right? Germany just declared that by 2020, they will be on 100% renewable energy. Zero nuclear. No coal, no nuclear, no petroleum. Wind, solar, geothermal, right? Now, that's an amazing thing because Germany is one of the biggest consumers of energy per person in the world because there's a lot of manufacturing, a lot of industry. So they use a lot of energy. And they just decided as a country, this is going to be our policy. It's amazing. No other country in the world has come forward like that. Okay, Journal of Engineering for Gas Turbines and Power. So we just talked about energy resources. This is a bit more specialized. Right? But gas turbines are found everywhere, including right here. That's a gas turbine. How does a turbine work? Who knows what a turbine is? What is a turbine? Turbine. What's the basic concept of the turbine? Yeah, it converts. Usually, it's used to either produce mechanical power, right, or electrical power. But when we call it a turbine, what does it do? What does it look like inside?
It's rotation.
Yeah, usually there's one shaft. And it spins, and off of the shaft are things like a big fan, like a propeller. So it's like a big fan. So if you look down a turbine, usually what you see, it looks like a fan spinning around. And turbines usually either accelerate or decelerate the gas that's flowing through them. Right? So in a jet engine, it does both. A jet engine has a bunch of turbines. These are all fans. Some air comes in the front. This fan is spinning around. It's powered. It accelerates that air, makes it even faster. It hits this fan, which accelerates it even more. And as it accelerates it, it's pushing more and more, so it also gets compressed. So it gets faster and more compressed. And these stages, there's sometimes something like 15 stages here. Now, when that's the idea, it's called a compressor. What comes out at the end of that compressor is air that's really, really dense, very highly packed together, lots of oxygen, and it's moving really fast. Then comes a section where you put some gas in there, and all that air is rushing by with the gas, and then there's a little fire, and it burns. And by burning the gas mixed in with the air, it causes it to expand, and now it comes really high pressure and really fast. And then it goes out the back through a bunch more of those stages. Only now it's doing the opposite thing. Each one of these stages is taking energy out of the air. So at this end, it adds energy to the air. It makes it denser, it makes it faster, higher energy. Then it gets burned, and that really adds a lot of energy. And now it goes through a bunch of fans. These are like windmills. And each one takes some energy out. It pushes this one, it pushes this one, it pushes this one. But they're all mounted on the same shaft. So the effect of all of that stuff pushing on these fans is to spin the shaft, and it powers these fans that compress the air. It becomes self-sustaining. So by adding the gas in there, you can power the front. And what's at the very front of this? At the very front of this, there's one great big fan. So here's the engine part. But if you look at the front of the jet engine on an airplane, when you look at the front of it, what you'll see is a great big fan. The engine part is a relatively small part of the middle. It's also taking air. It takes the air in here. Compress, 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 compress. Spin, 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 spin. But the idea is to spin the big fan. And the big fan blows all this extra air from the outside. It blows that air out here. It never gets burned. It's not part of the combustion. It's not part of the turbine. It's the thrust of the airplane. This is the thing that pushes the airplane forward, like a giant propeller. This is called a bypass turbine. Because most of the air bypasses, like 80 to 85% typically. 15 or 20% of the air gets burned. 80 or 85% of the air just goes past. And that produces the thrust that pushes the airplane. So a lot of people think that on a jet airplane, that engine is burning all of the air that's going through it. It's not true. It only burns a very small percentage. Most of the air is just a big propeller. Okay, anyway. So that's an example of a gas turbine. They're always used for power. Right? The electrical engineering version of this for generation, which is used in a lot of places, is, you burn gas. But at this end, to take the energy out, these fans are propelling a shaft that drives an electric generator. So instead of driving this big fan in the front, there's an electric generator somewhere. You know, it's an interesting energy challenge. You go out on the road and you see 1,000 motor scooters, right? All of those motor scooters have a small engine on them that's burning gasoline. Those engines have to be produced really cheaply because nobody wants to pay very much for a motor scooter. So you have a relatively cheap, inexpensive engine. It's not very efficient. Now, you could take all of those engines and say, let's get rid of those engines and make all of these motorcycles electric. Put a battery in there instead instead of the motor. And we'll produce all of the electricity with one very efficient, professional, large, expensive, perfectly built gas turbine like this. So instead of having 1,000 little pieces of combustion all around the city, have one place in the city where you have a good